Our goal for today is to do a few fun ideas related to Laplace transforms. We sort of have two big ideas and one baby idea. We'll start with the baby idea. So we're looking at an antiderivative. So notice here, f is a function. When you integrate from 0 to t of f of tau d tau, you have an antiderivative. So g is an antiderivative. And we're asked to say, what's the Laplace transform of g? Well, antiderivatives are tied to derivatives. And we have practice with doing derivatives, and so we're going to be able to use our tools that we have. So we say, all right, we know that the Laplace transform of f is something, we'll call it capital F. And then we say, well, because g is the antiderivative of f, f is g prime. All right, well, that's not too surprising. But then we say, we have rules. We have rules for derivatives. So we can say, look, the Laplace transform of g prime is s g of s minus g of 0. Well, what can we say about g of 0? Well, okay, come back up here. G of 0 is the integral from 0 to 0 of f of tau d tau. Well, 0 to 0, you don't go very far, and you don't do anything. So g of 0 is 0. So you say, great. So that's s g of s. And now, divide by s, and we get that g of s is f of s over s. And you're like, okay, wait, what? All right, so let's write this perhaps in a little bit slightly different way. So let's just say, what's going on here? So what we have is, what is g? Well, it's Laplace of g of t. So we could say the Laplace of the integral from 0 to t of f of tau d tau. Okay, so that's our g of s, right? G of t, I put it when what g of t is taking the Laplace transform, is 1 over s, and then it's the Laplace transform of f of t, because that's f of s. So it says, oh, so when you're doing an antiderivative, you divide by s. Similar in the way that when we did a derivative, we multiplied by s. So it's like, okay, this makes sense. I can believe this. This is good. This is good. But now we might say, okay, can we say anything else? Or is there another way to think about this? Because remember, rules for Laplace transforms can become rules for inverse Laplace transforms. And so what's the corresponding rule for inverse Laplace transform? Well, it would be the following. It would say, all right, if we wanted to do the inverse Laplace transform of 1 over s f of s, all right, so this is 1 over s f of s, well, that would be the integral from 0 to t of f of tau d tau. So inverse Laplace with a 1 over s becomes an integral. All right, good. So let's see an example. So here we have a problem. Find the inverse Laplace of 1 over s times s minus 3. Now, in the past, when we've seen something like this, we said, ooh, partial fractions. Now, going forward, when we see something like this, we're going to be, ooh, partial fractions. Because partial fractions is still probably a little bit easier way for us to do things. And, well, if we have something that works, let's go with it. This just says there's alternatives. And it's nice to know you have options. All right, so how do we approach this? Well, notice that this says the following. This is the same as the inverse Laplace of 1 over s, 1 over s minus 3. So when we see that 1 over s, we're like, oh, okay, so this 1 over s in the front stands for antiderivative. Or really, we're integrating from 0 to t f of tau d tau. Now, how do we find the right f? Well, we look at the rest of it and say, all right, what is the inverse Laplace of 1 over s minus 3? Well, of course, we know our rules. And we say, well, we know that. That's e to the 3t. So we put this all together and we say, okay, that means that this becomes the integral from 0 to t of e to the 3 tau d tau. Now, in some sense we're done, but let's go ahead and work the integral out, because this is an integral we can do. So let's see, this would be 1/3 e to the 3 tau. Evaluate that from tau equals 0 up to tau equals t. And if we do that, we get 1/3 e to the 3t. Let's plug in t. And then plug in 0. E to the 0 is 1, so minus 1/3, and we're done. That's it. And so we didn't have to do partial fraction. Now, if you did do partial fractions and ran it, you would end up at the same place. But this just says there's alternatives, and it's fun to know things. I always think it's fun to know things. That's why I like to know things. All right, so there was our fun baby idea, a nice warm-up. Let's get into our first big idea. So here we go. We start with, of course, our definition of the Laplace transform. We have f of s is the integral from 0 to infinity, e to the minus st f of t dt. And now what we're going to do is take the derivative of both sides with respect to s. Say, all right, great. Now you might say, is that allowed? Well, okay, let's get into it. First off, the derivative of f is the derivative of f, so that's easy. This is the derivative of s of the integral. Now, here's the part that's like, wait, are you allowed to swap derivatives and integrals? And it turns out that in some cases, such as now, you can't. You have to be careful because weird things happen. Mathematicians are really good at coming up with weird things that say, oh, but actually, but in this case, we're okay. So say, all right, we pass the derivative through. Say, well, look, where's the only place where that has an s? Well, the only place that has an s is this part e to the minus st. So you say, okay, so it's really the derivative of e to the minus st. We're taking the derivative with respect to s. So at this stage right here, ignoring the integral part, we say the t is our constant. So we bring the minus t down, and then e to the minus st f of t. The minus can come out. The t we can put onto the f of t, so it's t f of t. And then we're like, whoa, this is the negative of the Laplace transform of tf of t, right? Because what do we see? We have that we've plugged in tf of t into our definition of the Laplace transform. And so we have this really fun fact that if we take the Laplace transform of tf of t, we've really, this multiplying by t here turns into a derivative. So we're like, ah, cool. So we can actually repeat this and say, all right, well, what if we have higher powers of t? And we see that the same rule applies, which says, okay, every time you add a t, you add another negative, which is why you have a negative 1 to the n, and you add another derivative, which is why you have the nth derivative. And so now we have our new rule. So our rule really says tf of t. What do we do? But it also says, hey, how do you handle something where you want an f prime of s? What does that do? And so we have this fact. Now, I just want to point out something fun here. So let's go ahead and write this rule again. So we have that the Laplacian of tf of t is equal to minus f prime of s. But remember that there was this other fact, namely that the Laplacian of f prime of t, do you remember what that did? That was equal to our sf of s minus our little f at 0. Now, I love the fact that there's this beautiful symmetry here, right? So when we multiplied by a t, before we took a Laplace, it ended up becoming a derivative. Here, if you took a derivative, after you do the Laplace, you end up multiplying by an s. So there's these beautiful things that go along. In fact, most of the rules have this wonderful symmetry attached to them. All right, so what can you do with this? Well, we can actually do a lot of fun things. So we're going to go through and do a few examples showing how we can apply this particular rule. So let's start by finding the Laplace transform of t sine of bt and the Laplace transform of t cosine bt. Now here we can say, look, we have a couple of things we already know. We already know that the Laplace transform of sine of bt is, all together now, that's right, b over s squared plus b squared. And the Laplace transform of cosine bt, similar, is s over s squared plus b squared. Great, wonderful. Okay, so remember, when we multiply by a t, it says add a minus, take a derivative. So let's just do that. All right, so we'll start with sine of bt. So the Laplace transform of t sine of bt is negative the derivative of the Laplace transform of just the sine without the t. Well, that's our b over s squared plus b squared. Now for this one, we can take advantage of the fact, look, b is a constant, we can pull that out, and it's really saying take the derivative of s squared plus b squared to the minus 1 power. Now, so what happens? The minus 1 comes down, so minus 1 times minus b becomes b. Then we have s squared plus b squared to the minus 2 power. And finally, chain rule, don't forget the chain rule, chain rule. Derivative of s squared plus b squared with respect to s is 2s, or altogether we get 2bs over s squared plus b squared squared. And there we go. That wasn't so bad. All right, but of course, there's another one, and that's cosine. Okay, let's try that one on. Okay, so the Laplace transform of t cosine bt, well, what happens there? That's minus the derivative of s over s squared plus b squared. Now here, there's an s both top and bottom. All right, so we're not going to do the same thing we did up here. We're going to use quotient rule. All right, so let's see if we remember quotient rule. It's been a while, right? So you take the bottom, s squared plus b squared times the derivative of the top, which is 1, minus the top, s, times the derivative of the bottom. Well, that would be 2s all over the bottom term squared. All right, well, that wasn't too bad. Now, what do we have? Well, we have s squared, subtract 2s squared, which would make that a negative s squared, but there's also a negative out front, so that would leave us with an s squared. We have a b squared, but there's a negative, minus b squared over, and here we have s squared plus b squared squared. And there we go. That's it, right? So now the nice thing is we didn't have to do our integration rule. Can you imagine trying to integrate when you have a t and an exponential and a sine all together? Whoa, I would not want to do that. We don't have to because we have rules now, and rules make things easier. So it's nice to have rules, but even better than having them is knowing them and knowing how to use them. This is one of my favorites. So we're asked to find the Laplace transform of sine t over t. And there's a recall here. We need f of s to go to 0 as s goes to infinity. And you're probably thinking, okay, why is that there? Well, we'll find out. All right, so let's see what we can say. Well, what do? we want to find the Laplace transform. Now we say, well, we don't know sine t over t. Well, yeah, of course, if we knew it, it wouldn't be a problem. We'd be done. But what do we know that's close to it? Well, we know sine of t. So let's remind ourselves. So the Laplace transform of sine of t, well, that's 1 over s squared plus 1. Yes, we know that. All right, now how do sine of t and sine t over t relate? Well, it relates in the following way. So we could say, look, this is the Laplace transform of, we'll put sine of t over t, and then what do we need? Well, we need a t, right? Yeah, because t over t, that's 1. Great, those are equal. All right, wonderful. And then we say, but our rule now. We say, hey, if I have t times something, then according to our rule, this would be what? Well, this would be a minus, because remember, when we take t, that's a minus, and then the derivative of the Laplace transform of sine t over t, which is f prime of s. And now we're like, ooh, cool. So we have a derivative involved here. If we could solve for it, we'd be done. All right, so let's see what we have. We can now say that f prime of s is minus 1 over s squared plus 1. This feels really familiar, like we've seen it before. We have. Okay, so let's integrate both sides. And when we integrate, we get f of s is minus arctangent. What? Arctangent's in the house. Wow! Okay, so this is cool. Is this right? And what did I forget? I forgot something. Plus c, right? Because when you integrate, you have a constant. Now at this point, you're thinking, oh, well, you're in trouble, Steve, because what's your constant? Ooh, you're right. I would be in trouble, except they gave us something to recall. They said, hey, we need that f of s goes to 0 as s goes to infinity. Okay, so now let's let things head towards infinity. So as s goes to infinity, this side goes to 0, right? Because that's what this says. Fs goes to 0 as s goes to infinity. So here, s is going to infinity. All right. Well, c goes to c. That's no surprise. What happens to arctangent? What's the behavior of arctangent? So if we were to sketch arctangent, what does it look like? Well, it looks like a piece of tangent turned on its side. And so as we go to infinity, we are approaching an asymptote. Which asymptote do we approach? It is pi halves. And so we see that what? Well, we see that this part goes to negative pi halves. And so, well, now we can solve for c. c is pi halves. All right. And so we are done, right? Because we know c. So our answer is the following. We have that the Laplace transform of sine of t over t is, whoops, put that back, pi halves, our constant, subtract arctangent of s. Cool. Cool. Now, since we have time and we have space, bonus awesomeness. You know, who doesn't need some bonus awesomeness in their lives? Recall Laplace transforms, right? So Laplace transform of sine t over t, well, this would be the integral from 0 to infinity of e to the minus st sine t over t dt, right? Now, let s equal 0. What happens when s equals 0? So when s equals 0, what we get, well, we have e to the 0, which is 1. So we have the integral 0 to infinity of sine t over t dt, well, equals, we have to let s equal 0 on this side. Arctangent of 0 is 0. So we're left with pi halves. Wow! Are you serious? We are! This is actually true! It does work! Isn't it crazy? The integral from 0 to infinity of sine t over t dt is pi halves. We are so lucky that we kept up with this math thing. Can you imagine if we stopped after Calc 2? We never would have known this. You know, now our life is more complete. More complete, right? Because there's always more fun and exciting stuff for us to discover. Okay, that was one example. Actually, I think that was our second example. Can we do more? So let's look at this problem. We're asked to find the inverse Laplace of the natural log of 1 plus s squared over 1 plus s squared. I might say, wait, what? Well, I forgot to mention that upstairs there were parentheses around the 1 plus s. So the quantity 1 plus s squared. Downstairs is just 1 plus s squared. Now our first reaction is, we haven't seen anything with log. Do we have to go back all the way to the definition? No. Our goal is to use the definition as little as possible. At least I hope it's true that we can avoid that. And we say, well, wait, what do we have here? We have log. Now, one of the nice things about log is that it has a beautiful derivative. So in the back of our head we say, oh, maybe if we can use something about the fact that it has such a nice derivative, we can make that work. Okay, so that's our mindset here. All right, so we're going to think of this function as our f of s. Now let's take a detour and think about our rule that we've learned. And so just to see where we're at. So if we were to write our rule that we have, we say, well, what do we know? We know that the Laplace transform of t, f of t, well, that's equal to minus f prime of s. Right? That's essentially the rule that we've written down. But every rule for Laplace transforms becomes a rule for inverse Laplace transforms. We just got to sort of unravel it and think about what's going on. So let's take the inverse Laplace of both sides. If we did that, we'd get that t, f of t, is minus inverse Laplace of f prime of s. All right, well, we can move the t across. So that would say, oh, f of t is minus 1 over t, inverse Laplace of f prime of s. And you're like, okay, well, what is that? What is f of t? And how does it relate to capital F? Well, the answer is it's the inverse Laplace of capital F. So if I want to find the inverse Laplace of capital F, this says take minus 1 over t, inverse Laplace of the derivative. So if we ever encounter something that says, oh, this has a nice derivative, then we can use the derivative to find the inverse Laplace of the original function. All right, well, as we already mentioned, logs have nice derivatives. So we kind of have a plan now, right? We're going to take our function, take our derivative, and use the rule. So let's start by simplifying our function, because one of the nice things about logs is things can be made simpler. All right, so we can say, all right, f of s. Well, properties of logs, I can do the following. If I start, well, we'll start by copying. But whenever I have division, division becomes subtraction. So log of 1 plus s quantity squared minus log of 1 plus s squared. And then we can do a little bit here. We can pull this 2 down. So that's 2 log 1 plus s. We can't pull this 2 down because it's not the whole thing being squared, just a piece. And logs in addition do not get along well. It's unfortunate, but it's true. All right, so there's our f of s. Now we're after f prime of s. So we say, okay, well, let's find f prime. And because we've done our homework pulling things apart, it'll be more straightforward. So f prime of s, well, okay, so that would be 2. Now the derivative of log of something, you put the inside downstairs and take the derivative of that upstairs. So 1 over 1 plus s minus, okay, derivative says inside goes downstairs, derivative goes upstairs. And if we want to, and we do, we could rewrite this as 2, 1 over s minus minus 1. And you're probably thinking, why do you write s plus 1 in that weird way? We're anticipating doing an inverse Laplace. And here we'll write this as minus 2 s over s squared plus 1. All right, so we're now ready. Our pieces are in place. We can say the following. We have the inverse Laplace of our original expression, log of 1 plus s squared over 1 plus s squared, is equal to minus 1 over t, don't forget that, that's important, minus 1 over t, inverse Laplace of, and then we have 2, 1 over s minus minus 1, minus 2 s over s squared plus 1. And, well, that's minus 1 over t. Well, what do we have? We have a 2, and okay, that comes through. S minus minus 1, that's e to the minus t. And then a minus 2, s over s squared plus 1 is cosine t. All right, well, we can distribute the minus through and then divide by 2. And so we would get, since we're putting a minus, we'll reverse the order here. 2 cosine t, subtract 2e to the minus t all over t. And we're done. That's it. That's our answer. Isn't that cool? We're able to work things out so nicely now. I think it's wonderful. All right. Well, maybe one more example with this. And I think we can move on to the next idea after that. Use Laplace transforms to find a non-zero solution to tx double prime plus t minus 2 x prime plus x equals 0 with x of 0 equals 0. Whew! All right, cool. Okay, so, well, we have something to do, right? Well, let's start by, first off, rewriting this expression. So this is the same as tx double prime, and then plus tx prime minus 2x prime plus x equals 0. Now, let's think about what happens here. Okay, so we're going to take the Laplace transform of all of this. This is going to be fun. We have now the Laplace transform of tx double prime plus the Laplace transform of tx prime, and then minus 2 Laplace transform of x prime, and plus the Laplace transform of x. All of that equals the Laplace transform of 0. Well, the right-hand side, that's pretty straightforward. That's 0. Now, we have t times something. So t times something means take a derivative. So we say, okay, so here, this would be minus the derivative of the Laplace transform of x double prime. Here, same thing, minus the derivative of the Laplace transform of x prime. Now, the nice thing is, now we're into comfortable territory. Laplace transform of x prime, that would be s capital X minus x0. And Laplace transform of x is capital X, and then, of course, we set this equal to 0. Okay, good news. We know x of 0 is 0. Whew! All right, that's going to make our life a little bit easier. Now, let's see. Okay, continuing to work on this, we have minus the derivative of s squared capital X minus s x0 minus x prime of 0. So this is Laplace of x double prime minus the derivative. Okay, here it would be s capital X minus x0. And then, well, we have minus 2s capital X. That went away, plus capital X. All right, so now what do we know? Well, we know x of 0 is 0. So, okay, that goes away. That goes away. What about x prime is 0? They didn't tell us. And at this point, you're like, whoa, we're stuck. We're out of luck. Except we're taking the derivative. So it's something, it's a number, but when we take a derivative of a number, what happens? It goes to 0. So we're actually not as bad off as you think. All right, so let's work it through. So minus the derivative of the first, 2s capital X, and then, so derivative of the first times the second, we have a minus, and then the first times the derivative of the second. And then that's already 0, and derivative of a constant is 0. Similar over here, minus, okay, derivative of the first is 1, and then times the second, x, minus the first times the derivative of the second, x prime. All right, and then we have our minus 2s x and our plus x. All right. Okay, so what can we do? Well, now we can start cleaning up. We see there's a minus x and a plus x. Cancel. Nice. Unfortunately, the minus 2sx and the minus 2sx don't cancel. They can combine, though. All right. So let's see what we have. We have the following. We have minus s squared minus s, and that's times our x prime. And then minus 4sx equals 0. Huh. What do we do? It's a differential equation in terms of x and s. And not only is it a differential equation, it's a nice kind of differential equation. It's separable. This is a separable differential equation. Nice, 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 nice. Oh, we are so lucky. That means we're going to make more progress, right? Okay, so let's untangle this. All right, so what do we have here? Well, we can move the 4s across, and actually there's one other thing. Everything has an s. So before we do that, let's go ahead and divide. So think of this as minus s plus 1 x prime minus 4x equals 0. So this becomes minus s plus 1 x prime equals 4x. And now we can move things around. And we say, oh, this is the same as x prime over x, right? Divide, is equal to minus 4 over s plus 1. And we've done, essentially, it's a separation here. Now, if you prefer, you can think of x prime as d capital X over ds. And so you could also write this as d capital X over x is equal to minus 4 over s plus 1 ds. All right, and so we are ready to integrate because we've done our separation. Next comes integration. Isn't it great? It's like, what? All these ideas from way back at the start, they still work? Yeah, ideas are great, and they can, transcend time and space. All right, the integral of 1 over x is log x. Now, what's this integral? Well, it's negative 4 log s plus 1. Well, okay, and then of course you get plus some constant c. We won't worry about the constant right now. And, well, of course, notice it says find a non-zero. We don't have to find a whole bunch. So we can make a choice. Let's just choose our constant to be 0. Okay, why not? We can do that. All right. Now, if we didn't choose our constant to be 0, I'll point out that at the end, we would have had just some multiple of something. And so here, we can choose c equals 0. All right, so what do we have? Well, we can now, let's keep working. We can now say, well, that says that log of x, we can move that minus 4 in, so that's the same as natural log s plus 1 to the minus 4, or getting rid of logs, x is 1 over s plus 1 to the 4, right? Because s plus 1 to the minus 4 means you have a minus 4 downstairs. All right, so now we're in pretty good shape. What do we need to do to finish up? Well, the last thing we need to do is we need to solve for little x, not capital X. So how can we do that? We'll do an inverse Laplace. So we say, aha, idea, little x is the inverse Laplace of capital X. Well, that's the inverse Laplace of 1 over s minus 1. All right, because s plus 1 is s minus 1. Now 4, I'm going to rewrite this as a 3 plus 1. Now, you might say, well, why are you doing that? Well, because there's this nifty rule that says the Laplace inverse of n factorial over s to the n plus 1 is t to the n. So because we have our handy nifty rule, we say, oh, this is looking a lot like the inverse Laplace of t cubed. The minus 1 means we have a shift, so there's an e to the minus t. There's only one issue. We don't have a 3 factorial upstairs. Well, okay, so we'll put it there, right? If you don't have what you need, you put it in. So we say, okay, so you add a 3 factorial upstairs, you divide by 3 factorial downstairs, and now we're ready to say, look, this is 1, 3 factorial is 6, and we have our shift by minus 1, so that means e to the minus t, and then we have our t to the 3. If we'd kept our constant here, what would have happened? Well, it would have come in as a constant there, which would have been a constant there, which would have said we'd had a constant, so we'd end up with a constant. So really, we can take any constant multiple of this, and so let's just say e to the minus t, t cubed. There we go. There's a non-zero solution to this differential equation. And indeed, you can check it does satisfy x of 0 is 0. All right, wonderful. We found it. Good for us. Good for us. And it was a lovely walk down memory lane to visit separable differential equations. All right, so that was practice with our first big idea. Time for big idea number 2. Our second big idea is going to be somehow saying what happens with multiplication. It's not as easy as saying, oh, if I have a Laplace of a multiple of 2 functions, well, I'll just multiply each one individually. If calculus has taught us anything, no, that's not how it works. So how will it work? Well, we need to introduce something really quick. So I want to talk about something called convolution. And convolution is a way of taking 2 functions together and kind of multiplying them in sort of an unusual way. And here's how it works. We say that f star g, so we have 2 functions f and t, and we're going to create a new function called f star g. And the star here you should think of as multiplication because it is a multiplication of sorts. It's the integral from 0 to t of f of tau g of t minus tau, d tau. Now, you can, by a quick change of variable, show that f star g is the same as g star f, so it doesn't really matter which order you do this in. But what's the point here? Well, the point here is you have 2 functions, f and g. And what you're doing is you're sort of going in opposite directions and saying what happens as you overlap more and more of them. So initially you only overlap at 0, then you keep pushing them together, right? So here we're going from 0 to t for f, but then we're going from t to 0 for g. So it's like we're pushing in opposite directions and we're seeing what's the net result. Now, it's sort of like, why does this show up? And we'll see it actually naturally shows up when we think about what should happen. Okay, so what's our goal? Well, we have 2 functions, little f and little g, and we're looking at their Laplace transforms. Saying, all right, well, suppose we're multiplying capital F of s, capital G of s. Now, we know that these are Laplace transforms, so we know that these are what they'll be. And you'll notice we've swapped t's for x's and t's for y's. This is just to sort of set up what's going to happen. Well, if multivariable calculus has taught us anything, hopefully it's taught us a lot of things, it says, well, look, let's mush these 2 integrals into one single integral. And so that's what we're doing here. We're going from 0 to infinity for x, 0 to infinity for y, and we say, well, the fx, the g of y, great. Now here, the exponential functions, we can combine together. And we'll write this as e to the minus s x plus y. All right. Now, at this stage, nothing too surprising has happened. This next step is the big what? So that's why there's a dot here. Not to say that there's something suspicious going on, but this is the step that'll get it all. So where do we want to get to? Well, the idea is we're looking ahead and we say, you know, we'd really like this x plus y to act like t. And so we say, okay, so we want to think of x plus y is t. So how do we get there? Well, currently, the way this integral is set up, because we're going from 0 to infinity for y and 0 for infinity for x, what we're doing is we're really thinking of integrating along slices this way. And we're just going to add them up. So that's what the current integral does. And it says, well, wait, hold on, that's not quite the right way. If we want to think of this as being t, I want to think of x plus y as being fixed. So instead of slicing up horizontally, we're going to slice up diagonally. And by that means we're going to slice this way. And so you'll see that on these lines here, when you add x plus y together, you'll have, it's always t, right? So think of it as tau, t minus tau. When you add them together, you get t. And so, what's our idea? So we're still going to cover everything, but instead of our lines like this, we'll do lines like that. Say, okay, so what do we have? Well, we're going to let t go from 0 to infinity, and then for a fixed value of t, I need to go along the whole line. So that's going to be our tau going from 0 to t. So t goes from 0 to infinity, tau goes from 0 to t. And now you say, well, wait, what? How do all these things relate? Well, x plus y will become t. And the way it happens is x will act as tau, y acts as t minus tau. If you add them together, you get t. And so now it's our great aha. What do? Well, we just say, look, pull this e to the minus st over, and then separate off. And what do we have? Well, we have a Laplace transform, right? Namely, we have the Laplace transform of this thing, because we have an integral from 0 to infinity of e to the minus st dt. And now we're like, whoa, have we seen that before? Yes, it's what we just talked about. It's our convolution. It's f star g. So there we go. So our great aha is we can do a Laplace transform of a very particular kind of multiplication. So the Laplace transform of a convolution of two functions is the product of the individual functions. Now, of course, every rule for Laplace transforms becomes a rule for inverse Laplace transforms. So we would be remiss not to at least state that this says another way to think about this is if you want to find the inverse Laplace transform of the product of two things, it says, okay, you can do that, namely, it's f star g. So you do it by doing a convolution. All right, so that's the idea. Let's see some examples. So let's start with the following example. Find the inverse Laplace of 1 over s plus 2, s minus 5. Now you're probably thinking like, hey, partial fractions. Yes, that's how we would do this. And if we saw this problem in the wild, we would definitely go that route. But for right now, we're going to say, hold off on partial fractions. Let's get our practice in with our new idea. So what's our new idea? Well, we can think of this as saying this is really the inverse Laplace of 1 over s plus 2 times 1 over s minus 5. And now we say, oh, it's like we have a multiplication going on. And when we have a multiplication going on, that can turn into a convolution. All right, so what's happening? Well, individually we can find these. So the inverse Laplace of 1 over s plus 2, that's the same as the inverse Laplace of 1 over s minus 2. All right, just setting ourselves up. So this becomes e to the minus 2t. And the inverse Laplace of 1 over s minus 5, well, that's e to the 5t. All right, so here we go. We now have, by our rule for convolutions, that the inverse Laplace of 1 over s plus 2 times 1 over s minus 5 is going to be the convolution e to the minus 2t convoluted with e to the 5t. Now, we're not done. That's like cheating if you just stay, all right, I got something there. We got to keep going one more step. I'm saying, okay, well, how does one do such a convolution? Well, we're going to go integral 0 to t. And now we pick one of these to be the t, and one of these to be one of these to be tau, and one of these to be t minus tau. Doesn't matter which one. So let's pick the first one to be our tau, e to the minus 2 tau, and e to the 5 t minus tau d tau. All right, well, if we keep cleaning this up, 0 to t, this will be e to the minus 2 tau. Now here, I can think of this as e to the 5t and e to the minus 5 tau. Yes? Because I can break it up. Now, you might be thinking, oh no, integration by parts? No, definitely not. A couple of things, though, that we can do. When we look at this e to the 5t, how do we think of it? We can think of it as a constant, because it doesn't depend on tau. So we say, okay, pull it out. So that can go in front, e to the 5t. Now, on the other hand, how do we handle the e to the minus 2 tau, e to the minus 5 tau? Well, the answer is we push them together. And we can do that, right? Because we have rules for exponents. So we have integral 0 to t, and minus 2 tau minus 5 tau is e to the minus 7 tau. All right, good. Now, we're most of the way there. We're ready? We say, okay, e to the 5t, and now this becomes well, the integral is minus 1/7 e to the minus 7 tau, and evaluated tau equals 0 to tau equals t. All right, well, that's e to the 5t, and then we have a minus 1/7. Actually, minus 1/7 we'll treat like a constant, and then we have, what do we have? We have e to the minus 7t, and then e to the 0. Well, e to 0 is 1. Okay, so distributing this through, we have e to the 5t, e to the minus 7t. That leaves us with a minus 1/7 e to the minus 2t, right? 5t minus 7t. And then minus 1/7 times minus 1 makes a plus 1/7 e to the 5t. And there we go. We're done. That's it. And that's how it would work out. And you probably look at this and say, partial fractions feels faster, right? It might be. And isn't it great? You're like warming up to partial fractions. Who would have ever thought you'd get to the point where you say, hey, I'm kind of liking this partial fractions. I think I'll stick with it. But it's nice to see you have options and that alternatives work really well. Let's look at the example. Find the function f of t which satisfies f of t minus 1 is the integral from 0 to t e to the minus tau f of t minus tau d tau. And there is a hint. It says take the Laplace transform of both sides. Now you might be saying, wait, I thought we were doing Laplace transforms because it does differential equations. There's not a derivative in sight. Well, there's kind of an antiderivative in sight though, right? And the thing to keep in mind is Laplace transforms have existed for a long time before they were doing a lot of stuff with differential equations with Laplace transforms. In other words, it has many uses. And so essentially it turns out to be really good when derivatives are involved or when integrals are involved. It's just a way of transforming to take a problem from one setting to another setting. All right, so we're going to follow the hint. So let's take the Laplace transform of both sides. So we have the Laplace transform of f of t minus the Laplace transform of 1, all right, equals the Laplace transform of the integral 0 to t of e to the minus tau f of t minus tau d tau. Now, at this stage, you're probably thinking like, wait, how can we do this? Well, look at this integral. What do you see? It looks like a convolution. And that's because it's a convolution. So we see our f of t minus tau. So this should be a function of tau. So we say, oh, this is really what? It's the convolution of e to the minus t with our f of t. So that's the key, is to recognize the convolution. And of course, it's minus t and not positive t, because we want this to be a function of tau, that to be a function of t minus tau. So, okay, so let's, we'll write that down. Now, because it's the convolution, what this says is really we can do them separately. Namely, it's the Laplace transform of e to the minus t and the Laplace transform of f of t. So that's the great thing. Convolution becomes multiplication. All right, well, let's rewrite this and see what we have. So Laplace transform of f, we'll write that as capital F of s. And now Laplace transform of 1, that's 1 over s. And that's equal to, now here, e to the minus t, well, that's 1 over s minus 1. And here, Laplace transform of f of t is f of s. All right, good. Well, let's rearrange. So we can move things around. We get f of s minus 1 over s plus 1 f of s is equal to 1 over s. Yes, because we moved the 1 over s, we move this around, and minus 1 makes plus 1. Well, okay, so this is f of s times 1 minus 1 over s plus 1. That has to equal 1 over s. And let's see, what do we have here? Well, this would be s plus 1 minus 1 over s plus 1. Now, s plus 1 minus 1 is the same as s. So, okay, we have then s over s plus 1 times f of s is equal to 1 over s. All right, well, we're in pretty good shape, right? Now we multiply both sides by that reciprocal. So our function that we want looks like 1 over s times s plus 1 over s. Well, that's the same as, we can think of this as s over s squared, or 1 over s, and then plus 1 over s squared. So that's f of s. We wanted f, little f. So f of t is equal to inverse Laplace of f of s, which is the inverse Laplace of 1 over s plus 1 over s squared, which is 1 plus t. That's it. So 1 plus t is the function that does what we claim it does. That's actually pretty remarkable. It's a very simple function. And you know what? We like simple functions. They're one of our favorite kinds. So there you go. So let's look at the following problem. Find the Laplace transform of the integral from 0 to t of tau sine 3 tau e to the tau minus t d tau. And give your answer in the form of p of s over q of s, where p of s and q of s are polynomials. Now, what could we do? Now, one thing we could do is we could say, all right, we're just going to brute force find the integral, several pages of computations and algebra and calculus later. Fingers crossed, hopefully we make no mistakes. And then after we do that, we can take the Laplace transform of all the pieces that we ended up with and somehow push it all back together, and maybe we'd succeed. That sounds dangerous. Let's not do that. So what can we do? Well, what we can do is say, hey, what are some tools? Or maybe put another way, does this look like things we've been looking at? And it looks suspiciously like a convolution. So we say, oh, let's phrase it in terms of a convolution. So we have the integral of 0 to t of tau sine 3 tau e to the tau minus t d tau. Well, what's this? Well, okay, we see we have parts which look like it depends on tau, and parts that kind of look like t minus tau. So we say, okay, so this part, we'll think of this as our f of t, and this part we'll think of our g of, well, hold on, I said f of t, I want to say f of tau, and here I want to say g of t minus tau, and say, okay, what are our actual functions? Well, the f of tau, that's pretty easy to spot. That's t sine 3t. And now we're convoluting with, now here's the thing. This is tau minus t. I want t minus tau. How does one make a tau minus t look like a t minus tau? Well, the answer will not surprise you. It is, you pull out a minus sign. Ooh, okay, so this is really convoluted with e to the minus t. And now we say, hey, we have ways to do Laplace transforms of convolutions. So, what do we have? Well, the Laplace transform of our tau t sine 3t convoluted with our e to the minus t is the product of doing them each individually. So t sine 3t and e to the minus t. All right. Now, do we know how to handle t sine 3t? Have we seen it somewhere today? Yeah. Not just have we seen it somewhere before, we've seen it somewhere today. And the answer is we have. It's sort of our new rules that we learned today. So you take 2 times your b, in this case 3, times s, and then you divide by s squared plus b squared, 3 squared, squared. And e to the minus t, well, that's 1 over s minus minus 1. All right, so what do we end up with? Well, upstairs we have 6s. Downstairs we have s squared plus 9 squared, right? And then times s plus 1. And what do you see? Polynomial upstairs, polynomial downstairs. And so we're done. That's it. Now, in case you're wondering, was this on an exam? Yeah, it was. And see, once you know things, it makes things easier. We encourage you, know things. 4 out of 5 dentists recommend it. Know your rules for Laplace transforms. This brings us to our final problem. And I know we've been doing a lot today, and thank you for being patient. There's a lot of examples just to show you the broad number of ways that things can be applied. But this is the end for today, I promise. We're asked to find the solution for x double prime minus 6x prime plus 13x equals f of t with x of 0 equals x prime of 0 equals 0. All right. And in particular, express the answer in terms of an integral. All right. Well, how does this work? Well, what we do is we start by doing the Laplace transform of both sides. Say, okay, so this would be Laplace transform of x double prime minus 6 Laplace transform of x prime plus 13 Laplace transform of x equals Laplace transform of f of t. All right, well, we have our rules, so we use our rules. That's s squared capital X minus sx of 0 minus x prime of 0 minus 6 s capital X minus x of 0 plus 13 capital X equals capital F. Okay, now the nice thing is we have lots of zeros, and zeros are our friend. We like it when we have a lot of zeros. And that is to say, x of 0 is 0, x prime of 0 is 0, and so we actually have surprisingly not too many things here. So what do we have? Well, we have the following. We have just the pieces with the x left. So that's our s squared minus 6s plus 13 times x equals f of s. Or our function x that we're after is f of s over s squared minus 6s plus 13. Now, I will take a second here and complete the square, because the 13, that's just such a weird number to try to factor. This would be s squared minus 6s plus 9, right? Minus 6 divided by 2 is minus 3, so minus 3 squared is 9. Then we have 4 more. Okay, so this is f of s over s minus 3 squared plus 2 squared. Cool. Now, how do we get to our answer? Because we have to find a solution. Well, the good thing is we don't have to find explicitly, because we don't know what capital F is. We don't know what little f is. And depending upon what they are, it could be a lot of work or a little work. I mean, who knows? Who knows? But what we do know is that we can put our answer in terms of an integral. And like, the wheels in our head have been turning. So we say, hey, you know what? When we have a division here, we can think of it as really two things, as f of s and 1 over s minus 3 squared plus 2 squared. Right? So in other words, the division has turned into multiplication. Now, you might say, well, how does that help? Well, multiplication can become convolution. So, here we go. We can say that little x, which is the inverse Laplace of capital X, which is the inverse Laplace of these two pieces. So that's f of s times 1 over s minus 3 squared plus 2 squared. Well, that's really the inverse Laplace of capital F of s, convolution with the inverse Laplace of 1 over s minus 3 squared plus 2 squared, which, normally you wouldn't write all of this out. I'm just doing this just to emphasize what's going on, which is what? This would be little f of t, because that's where capital F of s came from. It's the inverse. The Laplace of little f is capital F, so the inverse Laplace of capital F is little f. And then convolution with our, now here, we have to be careful. All right, we have a 2 squared, so we have to be really careful here. So we need to put a 2 upstairs so that we have 2's matching. And so we'll have a half, that's okay. No worries about that. And okay. And then what do we have there? This is a 1/2, and it's going to be a sine of 2t. And there's a shift. So it'll be e to the 3t. All right, now notice this is not yet an integral, but we know it's a convolution, and so it becomes an integral. So this becomes our integral 0 to t of the first function with respect to tau. So I'll say f of tau, and then 1/2 e to the 3, and this function will be t minus tau. So 3t minus tau sine of 2t minus tau d tau. And we're done, right? Because we've expressed our solution in terms of an integral. Now, at this point, you're probably thinking like, really? This just doesn't seem like a win, but it is a win. Now, I do want to talk about a few things. I said this was the last problem, but I didn't say that I'd let you off the hook as soon as we got to the end. So there's something interesting going on here that if you look this up, if you say a textbook or other places, you might see something called Duhamel's principle. And which is to say, look, you can take this differential equation here with this function f of t and find a way to rewrite it in terms of an integral. And just with the right function attached here. Now, at this stage, you might be saying, okay, but have we ever done anything like this before? And the answer is yes, we actually have. So let's think back, way back. We're having so many flashbacks today to when we first started doing first order differential equations. So if you remember that, you had x prime minus, let's say ax is equal to f of t. Well, how would you do this? You'd find the integrating factor, which would be e to the minus at, multiply both sides by the integrating factor, integrate, solve for x. So if you carried out the work here, what would you end up with? Well, you'd end up with x is e to the at integral, and I'm going to use an integral as a standard for antiderivative, 0 up to tau of our function e to the minus a tau f of tau d tau. All right? Now, what can we do? We can bring this e to the at inside. So this becomes the integral 0 to t, and when we put these together on the inside, we get e to the a t minus tau f of tau d tau. Okay? So you look at this and say, oh, so when we were solving this first order differential equation, and by the way, I should add that this has the assumption that x of 0 is 0, we actually ended up with a convolution. We just didn't know it was a convolution at that stage. And it just turned out that the right function was e to the at. All right, well, now fast forward and say, hey, it doesn't just work for first order, it can work for higher orders. It's just you have to figure out what the right function is. So now, instead of the right function being maybe e to the at, maybe it's 1/2 e to the 3t sine 2t, and it just depends. But it's something that we've seen before, and so it's okay to say, oh, yeah, I can express this as an integral. Just as soon as I know my f, I plug it in, and there we go. All right, well, I think we can call it a day because we've definitely put in our work. We've learned a lot. We talked about, multiplying by t becomes derivatives. We talked about convolutions, and we've seen lots of ways that these can be applied. You want to keep practicing. You want these tools to become second nature and learn how to use them. The better you are at using the tools, the funner it becomes. Funner means you get to play around with things and say, oh, okay, how do I put things together? These are puzzles. Solve your puzzles. Get those points, pass the class, and become great. Because we believe in you. You are. You are great. See you again. Bye.